So a couple of more examples of U substitution. We need to be able to recognize a U substitution when it's in front of us. And so really encourage you, pause the video and look at this example on the screen and see if you can figure out what U should be before you watch it. So I'm thinking about this, and hopefully you remember that the derivative of arc sine is 1 over this radical. And so when you realize that, hey, this is a part of the derivative of this, then I'm going to try the upstairs thing as a candidate for U. So let's try U equals inverse sine of x. Then I know that the derivative of inverse sine of x is 1 over the square root of 1 minus x squared. See, when I see that I've got the derivative of this, I have the derivative of arc sine sitting here, then I want arc sine to be my U because I can get du, whereas you can't go the other way. So definitely want to try U equals arc sine. Du is 1 over radical 1 minus x squared dx. And so dx is just radical 1 minus x squared du. And so this problem becomes just u, the integral of u, and then actually it's just going to be the integral of u du. When you put the dx in, you're going to get the radical and this radical cancel, and you get integral of u du. So this is just u squared over 2 plus c. And, well, u was arc sine. So this is arc sine of x squared over 2 plus c. And that is the solution that we were after. I thought we'd do another problem. We're gonna look at some different variations of this same problem. So let's do the integral of dx over radical 1 minus x squared, and let's put the arc sine of x downstairs. So again, our goal is to develop the ability to see the U substitution. And in this particular problem, again, you're recognizing, hey, the derivative of arc sine is this guy. It's right here. There's a 1 upstairs, but I've got it. So that's a good candidate for my U in this case. So I'm going to, again, try U equals the arc sine of x. And again, du is going to be 1 over radical of 1 minus x squared dx. So if you want, you can say dx is radical 1 minus x squared du. And so you get, let's just work it out here in full detail. So I get dx becomes 1 minus x squared du over radical 1 minus x squared. Inverse sine is our u. So I get there. And so I get the integral of du over u, which I know is just the integral of 1 over u du. That's one you should have in your back pocket. Ln of the absolute value of u plus c. This is ln of the absolute value of arc sine of x plus c. Can arc sine be negative? Yes, it can. So you want to keep the absolute values on there. Don't drop those. So you're done. That's it. That's the antiderivative. So similar problem, but where where the arc sine was didn't really change the fact that that's the candidate for u that you want to try. Let's do another example or two. I don't want to do too many, but I think lots of examples with U substitution tends to help a little bit. So pause the video when I get this written down and have a look at this one and see if you can work it out yourself. What's U going to be? So we're looking for function composition, and we also want the derivative of our choice of U to show up as a product. And so here there is clear function composition, right? Your choice of U, hopefully you can see right away that U should be cosine of x, and du should be minus the sine of x dx. And so that means that dx is going to be du over minus sine of x. And so for this problem, you get what? You get minus e to the u du, so negative e to the u du, so this is just itself, so negative e to the u plus c, so negative e to the cosine of x plus c, and that's it. All right, so let's work out one last example, 11 problems. That's a lot, actually. the integral of the sine of 2x dx. And I want to show you two different solutions. So let's do this way first. So there's actually two ways to do this, at least. Maybe there's a lot more. I can think about, first off, doing a U substitution and setting U equal to 2x. And so if U is 2x, then my du is just 2 dx. And so dx is du over 2. And so I get the integral of the sine of u times du over 2. That's easy enough. So this is just 1/2 integral the sine of u du. So this is 1/2 cosine of u plus c. So this is 1/2 cosine of 2x plus c. There's my antiderivative right there. All right. On the other hand, you might remember the formula that the sine of 2x is 2 sine x cosine x dx. And you could do u equals sine of x. And so then du is cosine of x dx. Well, gosh, you've got that sitting right there. So I'm just going to write this as becomes 2, the integral of 2 u du. So you get you just get u squared plus c. So you get sine squared x plus c. And so those look pretty differently, right? Does this work? Let's check them. If we go backwards from here, does this work? Well, the derivative of sine squared, let's check d dx of sine squared x. This is going to be 2 sine x cosine x, which we know is exactly sine of 2x. So that one is certainly true. It works. Okay, what if we check this one? We take the derivative of cosine of 2x over 2, and we get, we're going to get the sine. The derivative of cosine is, minus the sine of 2x. Actually, we forgot a minus sign here. I forgot mine. This should be negative. So some of you have been wondering if I was going to catch that. Whew, thankfully I did. Negative, so then I'm going to get sine of 2x over 2 times the derivative of the inside is 2. These cancel, and I do get the sine of 2x. So, wow, interesting, isn't it? This answer, this indefinite integral, and this indefinite integral look really different, but they're actually the same. And what it's saying is this particular function equals this function plus or minus some constant. There are constants here that make these two the same, even though they look differently. So when you work out your problem in Mathematica or maybe some other software, the answer that they come up with might be different than yours. They can look different, but they are in fact the same. So let me end this video, and then I'll do one more where I want to look at some formulas with you.